Good morning, everybody. It's a real pleasure for me to introduce you to Maria Gritsevich, who is a good friend of mine and is a strong collaborator of our BOTES research group now here in Granada. And she's also collaborating with the University of Malaga. And that's the reason why she's also here visiting us these days. Maria Gritsevich is a prominent scientist known for her expertise in planetary science, with a special focus on meteoritics and planetary defense. In 2017, Maria earned a title of docent at University of Helsinki, which is equivalent to adjunct professor. And her academic journey started when she studied mechanics and mathematics at Moscow University, and then she got a degree in physics and mathematics at the famous Lomonosov State University in year 2009. Dr. Gritsevich's contributions to science have been substantial, encompassing a deep understanding of meteor phenomena and physical properties of meteorites, along with the potential hazards. Her research to be presented today in his seminar includes modeling of the dynamic meteorite entry into the Earth's atmosphere, evaluation of outcomes associated with asteroid and meteorites impact, and practical know-how of meteorite recovery. She has indeed helped recovery in several places, as she will tell us. And something also I should strengthen is that she has authored about 100 papers in leading peer-reviewed journals, contributed to over 200 extended conference abstracts and proceedings paper, and authored 5 book chapters. In tandem with her robust publication record, she actively participates in editorial work, having conducted over 120 reviews for journal publications or project proposals, where she's also heavily involved. Indeed, she spends part-time of handling editor duties, for example, as in the journal Meteoritics and Planetary Science, and having overseen more than 100 editorial editors today. I think that for us it's really an honor to have you here, Maria. And I mean, you are a person well known in the field, I know, and you have also collaborated with Olga at some point here. So we're looking forward to hear you and to keep the collaboration with you for the years to come. Thank you.
This blinking is okay?
The video is on my computer, so no.
Okay, thank you very much for the introduction. I will start my talk. Please feel free to interrupt me at any time. So let's keep with interactive if you want. So any questions are welcome at any time. So why are we interested in this subject? We have a lot of fireball networks worldwide, a lot of meteor registration, a lot of meteorite falls. So roughly I would estimate that we get like 1 million meteors registered every year cumulatively by different fireball networks worldwide, including BOTES, including the University of Malaga, in Barcelona, where is Spanish meteor network. And if you go to meteorite, if you go to museum worldwide, for example, in Vienna, there is a very, very nice museum and very nice meteorite collection. And you would also see that we have a lot of meteorite samples. So many meteorite samples, and I would roughly say 100,000. I think it's over 70,000 officially registered and many not registered. But if you want a meteorite with known history, so known trajectory, known orbit in the solar system, when we only have about 50 cases, which belong to both categories. So it's only about 50 cases that we have both trajectory registration and meteorite recovery, which I think is could be drastically improved by just applying some modern methods of processing. I will distribute here Chelyabinsk sample, so you could look how meteorites look like while I talk. I think many of you have seen, but you could have a look on these two Chelyabinsk meteorite samples.
This is the famous one that
Fall in Russia in
2015.
yes, 2013, 15th of February. So the idea is basically to match with communities. So there is a big data set of fireball registrations, big data set of meteorite recovered, but they almost don't cross. And this is the case of Sikhote-Alin recovered in Sweden in 2020. So this is our paper reference. You could read more about this case. And this is actually a very interesting case because, first of all, it was registered by our network in Finland, Finnish Fireball Network. Then it was also first iron meteorite which got instrumentally registered. And now I will show you on the next slide how it was going in the atmosphere. Yes, you could see. It was actually really, really low. It's also the lowest ever penetrated fireball because it went over 11.28 kilometers. And in the talk, I will first now talk about introduction, why I think it's important, then about method implemented to identify parameters, why I think it works or why we think it works. And then once we track the method, how to apply it more generally for the larger events. So a meteoroid is anything moving in interplanetary space and size is larger than an atom, smaller than asteroid. When this meteoroid comes to the planetary atmosphere, it starts to interact with air, produces a visible path, which we call a meteor. And most meteors in Earth's atmosphere are visible in the altitude range of 70 to 100 kilometers. We are now just about to publish a paper about meteors in Venusian atmosphere. It's also very, very interesting. It's actually, we estimate that there will be more meteors on Venus than on Earth. So we could get much more observations there. And fireball or bolite is essentially the same phenomenon as a meteor. It's just simply brighter intensity. So it's something much, much bigger and larger. And finally, some of these events, very few, will survive the atmospheric path and will land on the ground to be recovered as a meteorite. So a meteorite is something what is recovered on the ground. This is very nice illustration from our journal paper from Minerals in 2021. So I could explain you here now in more details, and you have a sample so you could look. Can you see my mouse? Yes. We have a meteoroid coming from orbit. So it comes to the upper atmospheric layers. It experiences preheating to the point where it starts to produce luminosity. So the luminous trajectory starts, and during this luminous phase, which we call meteor or fireball, we have major processes like light emission, mass loss, deceleration. It also has fusion crust formation. On the samples which I distributed, you could see the black fusion crust on top of the sample. So this is exactly what's happening here during this luminous phase. And it also experiences often fragmentation. So some larger fragments are formed, but also some meteoritic dust is lost, which in suspension could also land in form of micrometeorite. A smaller event we call a meteor, when we have also interplanetary dust, sometimes which lands without producing a meteor phenomena, and this is when micrometeorite, which also can be recovered. And this is intensive work we are now doing in the University of Malaga, studying micrometeorites. At some point, the fireball will vanish, disappear. This is happening because kinetic energy of the object is not enough anymore to produce luminosity. This could happen in two cases. Number one is mass simply is gone, so all mass got ablated, and even velocity was maybe still considerably high. is nothing, there is no body anymore, so there is nothing to produce luminosity anymore. And case number 2 is more interesting, because this is when mass is still left, but velocity is too small. So the kinetic energy is too small to produce luminosity. And this is when what we call a dark flight. So the meteorites would eventually land and form a strewn field. And this is also one of ongoing publications from us about strewn field. Strewn field is not actually an ellipse. It has much more elaborate shapes, and thinking that strewn field can be approximated by a line, as it is often assumed, or an ellipse, is not very accurate approximation. So this is where we also take into account winds and calculate where different masses with different shapes and different densities would land using the winds for specific events. It's also maybe important to notice that when luminosity ends, there will be still a small portion of trajectory when ablation is still continuous. So it's not instantly it's switched off, but very soon after the terminal point. There are many ways to detect fireballs, and I think there are more, but we could maybe list with main. So first, with telescopes, radars. There are now a few asteroids which were registered just before they hit the atmosphere. So sometimes for a large meteoroid, it's possible to register it a little bit in advance. When we have radars, I am collaborating with a group in Kiruna in Sweden. They have very powerful radar. So the peculiarity of radar is that the observational volume is very limited, but when you get very, very detailed scan of every single particle with the sensitivity, which is impossible to get with optical devices, at least not today. When we also get sonic booms, we have infrasound seismic registrations, especially in case of meteorite falls. And also in US, we were very successful using weather radars. This is when during the dark flight, after the fireball terminated, in weather radar, you can see specific peculiarities in the wind or in the air directly. So this is now what's going on with the fireball networks and meteor detections. But if you look in the past, you would see that impacts have shaped significantly Earth and other planets and moons in our solar system and probably beyond. So if you look in the past, this is what could eventually happen. So this is the largest verified impact crater on Earth in South Africa. It's called Rutherford, and it's 300 kilometers in diameter. And when we have Barringer crater in Arizona, also very famous, was formed by Iron Canyon Diablo meteorite, and it's about 1.2 kilometers in diameter. So interesting because you could see it's a very well-shaped structure. Impact of a solid object, which basically goes without notice through the atmosphere, it doesn't fragment, it just makes one big crater and meteorites. And this is similar, to me, it appears similar, Lonar Lake in India. It's 1.8 kilometers, so also same. One crater, very well formed, and a lot of meteorite fragments. When a group of events like Sikhote-Alin, for example, a large iron object comes to the atmosphere and it fragments, it produces a lot of meteorites and a lot of craters. So it's a little bit different. And this happened in Russia in 1947. A lot of stones, a lot of fragments were recovered. And when we also have cases like Tunguska, so a large object comes to the atmosphere, it loses mass so effectively that at the time of reaching the ground, there is no mass left, so no meteorites were recovered. But the shock wave reaches the ground and it destroys a huge patch of forest. So this is how Tunguska is looking still nowadays, like after 100 years after event. It happened in 1908. And you see it happened in remote Siberia, but if it would happen 3 hours before, it would hit a city like Moscow and it would totally destroy the whole megapolis. So it's a big thing, and at the end of this presentation, you will understand why actually different events, different fireball events, may produce with seemingly different consequences. Another reason why we are interested, all of you know that now space agencies are actively involved in so-called sample return missions. One of them can be Rosetta, and in case of Rosetta, €1 billion was spent just to send a mission to comet Churyumov-Gerasimenko to maybe get a sample, analyze back in the lab. So of course they get spectacular images of the comets, and our knowledge is significantly improved, but it costs a lot. In this case, this is very complementary to sample return missions. The only difference is that in sample return mission, you are planning in advance. It's usually 30 years planning, and you are thinking, all right, which will be the target? Which sample do we want to bring back? And in this case, a lot of samples are choosing us. So the samples are choosing us. And it's up to us to just observe it, calculate it, go to the field, pick it up, and bring it to the lab. And that's basically almost free. Because this is so interesting, organize so-called multi-station observations. And from multi-station observations, what usually is the usual like parameters which get calculated are meteor height. You get stations spaced, say, 200 kilometers away, ideally, or 100. And when by triangulating, you get meteor height, position. So you get the trajectory. You also get length along trajectory. And from these separate lenses, you calculate the velocities. You get meteor intensity, how bright fireball was, if you engage with light curves. You also get spectrum. So you could also get spectrum if you use special equipment. And first such project was done in Harvard. It was called Harvard Meteor Project, and it was done by a famous astronomer, Fred Whippler. He started in 1936, ended in 1951. They collected a lot of orbits and there are some publications, but they didn't recover any meteorite. So the first successful meteorite recovery project was done in Andreev, and it was led by Zdenek Ceplaka. They started in 1951, and bright fireball was photographed on April 7, almost like today, 1959. And following this registration, 4 meteorites were recovered near Przybram in Czechoslovakia at this time. So this is, you could see the registration of this first fireball, which led to meteorite recovery. And these were the 4 pieces which got, so one got broken after being picked up. And since then, as I explained to you, over around 50 cases now with known orbits. One would expect we would have much more, but this is the reality. It's now statistics is improving. I couldn't fit the whole list here, so it's Matthias Mayer has very nice web page here which you could visit for all these. So now what we can do with the data. When we have ground-based observations, so to give you a simple touch how it looks like, these were the images I still work during my PhD, but these are good representative images. Usually what you get as input parameters to model really the event, to understand the event, is fireball brightness, so how bright it was, intensity, height, and velocity. And you could see that, for example, in European fireball network, they use this rotating shutter on top. So the shutter would make this kind of breaks. And when you know the periodicity of the shutter, so from these breaks, you would estimate velocity at different point of times. And these are shown cases here is meteorite Neuschwanstein, famous meteorite from Germany, which was recovered. And this is Innisfree from Canada, Canadian meteorite and recovery project. And now for interpreting fireball observations, there are a few methods. I will briefly touch photometrics, and I will mostly explain dynamics. So in photometric method, it is rightfully assumed that part of changes in kinetic energy with coefficient, luminous coefficient tau is converted to luminosity. And this is good. And we studied this, so it actually gives good result. But usually what is happening in the field is that most people say, well, velocity didn't change that much, so we actually could decide that velocity was constant, so deceleration was negligible. And then by substituting this condition here, you could get changes in mass instead of change of kinetic energy. And when you could, this is what you would call photometric mass. So when intensity is directly converted to photometric, and sometimes it's good, but oftentimes it's not so good, especially in case of meteorite falls, because then you really have to look also in changes in velocity. And we did the analytical study on this, and it works. It's just a little bit more calculations, so people don't like it. But this is published in Icarus in 2011, and it gives good result. And also some follow-up studies are available now. And sometimes people also mix these two, like photometric and dynamic. I personally prefer not to do it, because when you have too many free parameters to fit, and you could do, as I will show you now, without completely not assuming anything. So the parameters will be combined in such a way that you don't need any assumptions, and you would arrive to meaningful estimates. So in dynamical case, we have these equations, which are considered. First one is basically second law of Newton. Mass multiplied by deceleration is equal to the sum of the forces. And the Moynihan force is drag force. So we have here drag coefficient CD, density of air, velocity to the power of 2, and cross-section area of the body. Cross-section area of the body is something that body is moving along the trajectory. And if you take a plane perpendicular to the trajectory, this is your projection of your body, will be called cross-section. So when simple geometrical relationships, which is only used to get rid of time. So now we will pass on the next slide from time to height. And then slope of trajectory is here. And the last one is describing how mass is changing with time. So the effective destruction enthalpy is how much is showing the rate of mass loss of a unit of mass. And here we have similar relation to the first one, except we have heat exchange coefficient here, and we have velocity to the power of 3. So now with this second equation will be used to substitute time with height here and here, and we will be left with two equations. So we are left with two equations. I rewrite them in this form. And then what is really important and powerful is getting rid of dimensions. So we are getting rid of dimensions. I really try to minimize this, but it will stop soon, don't worry. We will get rid of dimensions. And so now instead of using mass, we will use normalized mass. We divide by initial mass, pre-atmospheric mass value. So instead of dealing with mass changing from ME to 0, we are now dealing with M small, changing from 1 to 0. So we normalize velocity with initial velocity value, and we normalize height with height of the homogeneous atmosphere. This is constant for every planet. It basically means that if you take a planet and its atmosphere, and if you compress the atmosphere so that the density is constant everywhere, you get a constant for each planet. So we need this one. When we scale cross-section area of a body with initial cross-section area of a body, and we scale the density of air with gas density at sea level. And then you could see that we have two equations and we have 5 variables, 5 parameters. So if we want to find analytical solution, which is possible in this case, we need 2 more equations. And this is easy. Because if you think about it, the way cross-section area changes, and mass is changes, they correlate. So these two parameters are related, and it was proposed already 50 years ago or even more by Yuri Levin. So that there is mu which can be used. And this parameter mu is often called shape change coefficient. So why shape change coefficient? I will explain it easily. So if you have mu equal to 0 here, any number in the power of 0 equals to 1, which means that your cross-section mass is lost, but cross-section area is constant. When is it possible? This is possible when your body is moving, or if your movement is oriented, and when cross-section area can be approximated as a constant, but all mass is lost from the frontmost point. So you are kind of going like this, you are keeping the size in cross-section area, but the ablation goes from the frontmost part very effectively. And in the other case, limiting case, so the mu is equal to 2/3, and this is when shape of the body is constant. So the shape of the body is constant means that body would rapidly rotate, and ablation would take uniformly in place in all directions, so that your shape will be constant. In most studies, people just say, "Oh, shape is constant," and this is, but it's so easy to have this mu, and in case of keeping the mu, what happens is that it could be usually between 0 and 2/3, and it can be anything. So I think it doesn't make any trouble to keep it. And when you really allow for shape change during the trajectory, and what you could also do, you could recover this mu from light curve analysis, what we've done with the other papers, which I will not cover here for the sake of time. And other two parameters which correlate is density of air and height. So it's clear that when you go upper, the atmosphere becomes rarefied. So you could use this exponential atmosphere as a simple analytical approximation, but you could also use any arbitrary model, and we have a separate paper about it with ESCO. So you could go to this paper and read how to do it for any atmospheric model, but I will just cover today exponential. And if you use now these two equations, you could solve with differential equations I had analytically. And the beauty here is really we didn't have to assume anything. We didn't have to say, oh, drag coefficient is this, or heat exchange coefficient is this, or body loses masses like this. This is what usually happens. Really nothing. So this is the beauty of it. When we take first integrals, we need initial condition, and the initial conditions used here is like this. Body comes from very far, infinite height, and in the beginning, it has initial velocity and initial mass, super easy. Once you introduce these two differential equations, you get these two equations. I think it's my last slide with equations, so. This is, the first one describes how mass is changing with velocity. So this is how dimensionless mass is changing with dimensional velocity. And the second one is explaining how height is changing with dimensional velocity. So, and you see that here we have now three parameters, alpha, beta, and mu. Mu, I just explained, is a shape change coefficient. And the alpha, beta, I will explain in the next slide. They emerged from this dimensionalization what we were doing. And also here, there is this special function called exponential integral. Some people are afraid of it, but it's really easy. It's just some function you could find in any textbook. This is how it is defined, and there is also Taylor series, which is super easy to handle in calculations. So we have this two analytic expressions now: how mass changes, how height changes, and I will explain what alpha and beta means so that you understand. So the alpha and beta emerge from our dimensionalization, and they include many of the unknowns we don't know, like mass, drag coefficient, cross-section area. So if you would take a time to think a little longer about it, you would understand that actually what's happening is that instead of having 8 parameters and assuming 6 of them to derive the other 2, we have a combination of these parameters, and now this combination can be derived in unique way, and we don't need to assume anything about it. And if you look into the definition for alpha, so this is what we call it ballistic coefficient alpha is composed of. You would see that so alpha is actually shows a ratio between 2 masses. We have mass of the air here, or mass of the entry mass of your body here, and we have here mass of the air in front of the object, because this is, you see, this is density of air at the sea level multiplied with height of the homogeneous atmosphere, and then with cross-section area of the body, and then you divide it by the sinus of slope. So you really, it literally shows you, if body comes to the atmosphere, how much air it has to push through to reach the ground. And now you look how much is this air if you divide it by the initial mass of the body. So we don't look exactly what's the mass of the object, but we look what's kind of effective mass. So how much is the mass of what the body has to go through divided by the mass of the air. It's the ratio of masses, and you will see how effective it is in characterizing fireball events. So similarly, we have this massless parameter beta. Now, if you look into definition of this will be ratio of kinetic energies. So beta will show you how much is kinetic energy of the object at the entrance, at the entry to the atmosphere. If you divide to how much energy you would need to fully destroy this object in the atmosphere. So this is where your material properties come to play. So if alpha is not sensitive, alpha is only sensitive to masses, what's the rate of mass? So here you would have a huge difference if your body is made of iron, of stone, or of ice. Huge difference, you would see. And this is you will see later how this plays a role in understanding meteor phenomena, because if you just say, okay, this is the object comes with this kinetic energy, it's not so representative as beta, because it really could be made of anything. And when 1 ton of ice and 1 ton of iron would have very different property, very different outcomes in the atmosphere. And now what can be done, like to put it in a simple way, we have, when we have meteorite fireball registrations, this is example of Innisfree meteorite here. So the observation data can be processed into a table which has time, height, and velocity at different points along the trajectory. So on the one hand, we have how time, height, and velocity were changing in our observations. And on the other hand, we say, okay, if we trust this theory, then height should change with velocity according to this law. So the solution is super simple, just to compare this equation, how height and velocity should be changing in theory with points from observations, for example, using least squares method. And then from this fit, you get just unique, just one alpha and beta pair, which fits to every fireball event. So every fireball table like this could be fitted with alpha and beta, which provide the best fit for the solution. And this is what we will be seeing now, how this is used. Now we have also modified this method. So we have actually applied it to partial trajectory registration, and it also works, because this is what you need for radar. Radar doesn't detect the beginning of trajectory. And for other data, but we have super nice, very fine resolution. So we have very nice resolution of data, but it's part of trajectory. And we try to fit with method, and it also works super nicely. So you could see that all data are very aligned. And even so we didn't catch the beginning, we can actually reconstruct it by using this. So apart from what I have shown, there are a few nice reasons, which at least for me is pleasant to see why I think this works. First is pre-atmospheric size estimate. We collaborate with few groups who analyze meteorites in the lab. One of them is in University of Bern. So the Swiss people. And when what we're doing is when meteorite is recovered, so we pick up a sample of meteorite, we make a thin section, we bring it in the lab, and in the lab we do cosmogenic radionuclides. And from this cosmogenic radionuclides, we're able to deduce the size of the object which was before hitting the atmosphere. And so far, it's incredible because everything we did, it's totally independent estimate. So we do chemistry in the lab. I do trajectory interpretation in computer. And when the masses what we get or the sizes what we get are pretty much same so far. So this was done for several cases now. For Košice, we got results which was almost scary to publish because the difference was like, I think it was like 150, like 10 kilograms maybe difference. So it was like less than 1% difference. It's crazy. Then also we had with Joseph Trigo Rodriguez's student, Manuel Moreno Ibanez, and we were doing with terminal height calculations. So I had this idea that we could also estimate the terminal height, which I like because apart from terminal height, it would imply that you could actually estimate the duration of fireball, and nobody did it so far. So if you have event which would come to the atmosphere using this method, you would be able to say at which point it would terminate, which I think is important because so far nobody was looking into this. And what we did with Manuel is that I just gave him a bunch of calculations of more fireballs, and I said, imagine you know nothing about this fireball. So imagine you have no observational data, and I only tell you alpha and beta for each event, and tell me when we would terminate. So he computed with terminal height, just using this theory. And when we compare to real observed terminal height from these events, and in all cases, we got super nice match. You can see they're all aligned. So this is like computed and observed, which is incredible. Apart from the few cases here, which are actually meteorite droppers, and which have very simple explanations, because for calculating with terminal height, we assume that mass is 0, but mass was not 0 here because something dropped. So these are meteorite producing events. And then, of course, we have now a few meteorite cases recovered. So I will just show you one, which was happening in Finland. So these methods are applied in Finland for the processing of the data of the Finnish fireball network. We have a network fully run by amateurs. It's an amazing job they do. And it was in 2014 that we got this registration of Annama. Was registered by several places. Many people who saw it by own eyes reported to Finnish popular web page. And this is one of the images we got from Finnish fireball network. And the second image, this is how fireball was going. But images from Finland were not so sufficient. So we looked online and we were able to find a video in YouTube from Snezhnogorsk. And when we were able to reconstruct the trajectory here, we only didn't get the end of the trajectory, but it was enough for us. So we got with 3 Finnish stations and one video from Snezhnogorsk. I will show you now this video. It's short. Yes, so this was a video, and it's really amazing that I think we found this video on YouTube. We were able to reconstruct which city it was, which street it was, where car started, what was the speed of the car, and then calibrate the camera and get it to the point that we could really get exact trajectory. So Jupiter was found on the sky for calibration when horizontal and vertical lines reconstructed. and do it to the point that we could actually estimate the trajectory and send people to the field to recover the meteorite. I think it's amazing. So this is the kind of popular article in our Finnish popular astronomy magazine, Target Avaros, and it was published still before the meteorite was recovered. But it gives you a good illustration of the fireball path. So this is the alpha beta feed. As you could see, this is the observational dots here. And the line, you could imagine that this is the fit to the dots, but this is not the fit to the dots. This is analytical solution, which I was showing before with alpha and beta. It just provides such a good fit. Just provides such a good fit. So these are the results of calculations, ballistic coefficient and massless parameters, beta, masses, terminal mass and initial mass. And you could see that if I would compare at this time to the available meteorites, which were much less than now, it would be very similar to Innisfree, extremely similar. So it was clear for us that we should do very detailed dark flight calculations and try to go to the field and recover. And this is what we did. So there was this dark flight calculation made. Many fragments were forecast with different masses. And then I have here a zoom up of this area. So you could see in this zoom up, these are two fragments which were recovered, 120 grams and 40 grams. And these are predicted masses, so we're very close in very proximity of this area. So with this strong field, we sent, I was in contact with my friends in Ural Federal University because we already collaborated in Chelyabinsk a year ago. They trusted and they said, yes, we will go. We will go. And then there was also Thomas Kohut from University of Helsinki who joined the expedition. So 4 people. They came to only for 3 days, and the first day they didn't find anything. They just arrived to place and so on. And next day, Nikolai Kruglikov, who is here on the photo, he saw the meteorite from the car. I think it's amazing. He saw the meteorite from the car. It was just on the ground. Somehow he just managed to spot it. It was recovered very soon. So the fireball happened April, and this was recovered in May, and it has 0 weathering grade. Okay. And then next day we just follow the same area, and then in the morning we found the second sample, and then they just had to go home because we only booked for 3 days. Okay. We did immediately all analysis of the samples. This is published now. Also, orbit could be calculated with our Meteor toolkit software. So this is where the meeting point with the Earth. Yes. So if you think you can trust it, you could apply to much larger data sets, and we did to many now. Freeplon, different fireball network in Australia, Finnish, Spanish. So there are a few publications now about this methodology, but I will just explain you how it works, and you will see how easy and beautiful it is, I think. So you have, what I have here on this plot is logarithmic representation of alpha and beta for different fireball cases. And here I show you example of Canadian MORP, Meteorite Observation and Recovery Project, fireballs. So I have here logarithmic scale, so logarithm alpha and logarithm beta. And then for each fireball event published by this program, I calculate alpha and beta and put it on the plot. So I take next event, put it on the plot, and just calculate all. And suddenly what I discovered then is that there is only one meteorite that we recovered. And for this meteorite is the leftmost point on this plot. And this was interesting. So it actually means that it's not the meteorite with the biggest mass, but it's the meteorite with the smallest ballistic coefficient. So it was a meteorite. It was a fireball with most optimal ratio between the masses. So mass of the air divided by the mass. This was most optimal, very favorable for meteorite recovery, and this is why it was recovered. And if you think more about it, it is actually possible to construct the curves which would separate meteorite production from fireballs which would fully ablate. And then for these curves, you need some kind of analytical definition what is meteorite, and depending on this definition, it may change. So here I tell to machine, I call meteorite anything which is at least 8 kilos, and this is the curve that would be built. It's also slope sensitive, so. But anyway, the idea is that for now you could actually, for each fireball event, you could calculate alpha and beta and plot this curve. It's just jumping, I didn't touch it. You could plot, you could calculate alpha and beta, you could plot this curve, and based on your graphical representation or analytical, whatever you prefer, you could decide is it producing meteorites or not. So this is super important and super fast, and you could do more detailed follow-up later. But this is handy in this sense that now when we register so many fireball events every year, you could just run it automatically and decide which are interesting cases and which are not so interesting. And now coming back to the events which I was showing you in the introduction. So you remember I was showing you this Barringer crater, Canyon, Diablo, Meteorite, Tunguska, Sikhote-Alin. We could see how this would look on the plot. And on this alpha beta plot, they would appear like this. So Barringer crater is somewhere down, so it had very low mass loss and very low ballistic coefficient too, so huge mass, and mass was not lost practically so much. When for Sikhote-Alin, well, it's a little bit less mass and also, or at least a higher ballistic coefficient, and it was also losing mass a little bit higher, so it was fragmenting. And then Tunguska is somewhere up. I wanted to specify that this is logarithmic scale. So my origin corresponds to the point where both parameters are 1. And this is the area where just parameters are very small, but positive, very positive. And now what, in this plot, I could draw the 2 lines. So one line would show the area where meteorite are produced. So this is meteorite producing curve. And the other line is another paper, which was also published, is production of craters. So now what's looking at this plot, if you have a fireball event, you have alpha and beta calculated, you drop this point on this plot. And if you end up anywhere below this red line or curve, you would have a fireball event which will produce meteorites and also produce craters. If your event is in between these 2 lines, so you would have meteorites survived, you could go to the field, recover meteorites, but energy would not be sufficient to produce a crater. And finally, if something is above this line, then you have fully ablated case, so fully destroyed in the atmosphere event. This explains why Tunguska, even though the mass was so huge, but the mass loss was so intense that eventually when it reached the ground, there was nothing to be found in form of meteorite. And this is where our Annama star fits magically. And most of this kind of present-day meteorites which have registered trajectory, they also cluster around this area. And this is where Chelyabinsk fits. This is unpublished, but yes, it's a very nice, it's almost like Etalon around 1-1. Yes. This is example of a desert fireball network. What I really like about desert fireball network, apart from they have a really great team working there, it's very easy. You go, it's a desert. So, you know, if you calculate something and you go to the right place, you really recover it. And so far, all meteorites that they have recovered, they are identified here and they fit. So it's very nice and easy because we have a lot of registrations, good skies, a lot of cameras, and now a lot of meteorites too. So the alpha beta can be used to determine consequences of an impact, to model the event, They could be also used as an input for light curve modeling, which I didn't touch here. But if you do it, then you could also say about rotational rate. So it could be used to identify meteorites, craters, airbursts, other peculiarities. And our success cases now include meteorite recoveries in Annama, Ozerki. Also, Odalen in Sweden was quite rightfully predicted. This is very easy to apply to big data. We have many pieces of software, so if somebody is interested, we are sharing it freely. I could give you something or guide you to the right place to get it. Something was published in this book with Joseph Rodriguez, Assessment and Mitigation of Asteroid Impact Hazards, which you could get. And something, of course, in form of publications, which I included just some. But yes, here it is. I think it's probably all. I also wanted to thank you to Esko Lutinov because I'm so grateful for meeting him. He was amateur, but I mean, he's a genius, and we did so much nice discussions and papers together. So he's really great man, and he was behind the Finnish Fireball Network for many years. And the ideas what we share together is just out of this world, really. Yes, grateful. Also, now I'm continuing his work about cometary dust trails, and this is also amazing. So sometimes it's nice to work with people outside academia. I don't know, I wouldn't even call it, because they have very unique vision and ideas, and it can be just wow. Yes, thank you.
Thank you very much, Maria, for this wonderful talk. It's really impressive what you have shown us. A nice explanation of Tunguska. That's why you can produce meteors, meteorites, and craters. The basis of the alpha. So I would like to ask whether there is any question from the audience. Or maybe the remote assistance. Okay. In the meantime, I can ask you about, can you briefly tell us about micrometeorites, why they are important to study, and what you are doing with the University of Malaga in that regard?
I think they show different degree of melting, and I think so different processes. It would be important to see which produced kind of maybe meteors, which not. What was the interaction with the atmosphere? But I think the main reason why it is so interesting, you see, it's recovering meteorite. You really need kind of fireball network, and you need observations and processing observations, and you need manpower to go to the field to recover. But with micrometeorites, you need basically imagination in place, and then go to the roof and pick up it. And it's very likely that if you are persistent and determined in what you want to find, it's very likely that you can find it. So you could study micrometeorites without having a dedicated network. You could just have a dedication. And I know Jon Larsen, he was coming for a visit in Helsinki last year. We collaborated, so he gave some samples. It's amazing. I think I gave you his book, yes. I think his work is also truly unique. So a lot of people, most scientists were thinking it's impossible, but he proves it's possible. So micrometeorites is now, I think, is a rapidly rising field, and you could recover many of them. Any of you could go and recover many of them, and we are just learning what can be done. And it's amazing. You look, it's really like dust. It's dark, and until you look under a microscope, what we did also with Rosa in Raman, and now with Javier Lacerna, he might have very unique instrumentation in the lab. And when you look, and it's just an work. It's almost like a planet, and it's we are also different. It's unbelievable. So for me, I think it's very interesting. It's very interesting.
Mm-hmm.
Yes.
Perhaps it's an question, but I'm curious Is there any possibility to take a spectra of micrometeorite, for instance, that they are more often? Sure.
You mean spectra like of micrometeorite which is already collected?
Having some hole and taking spectra and have very.
You mean in the lab or oh, from trajectories? I think we're too small. The micrometeorites are just too small. They're like yes, they're micro size. But I don't know. We were discussing last week with Emilio, who is a robotics engineer, some possibilities of interstellar detection, because I'm thinking, so this could be a possibility, maybe something. But of course there are some options. I think we should always think big and like beyond what's already achieved of whatever crazy ideas, because this is way forward. Especially now when technology and software and the hardware so rapidly developing. We should keep monitoring.
Anyone else? Olga?
Maria, what's has been a hot topic in the last weeks?
Yes.
How do you distinguish whether a fireball is produced by a natural object or something else?
Velocity is different.
So is
Usually,
it possible?
velocity is usually different. So usually, if you have a space debris or some re-entry, it's usually low velocity. So in our case is usually from 11 to 72 kilometers per second. Okay, I see Eloy is here listening online. So with Eloy, we just published another paper on hyperbolic. We have registered one hyperbolic in Finland. It was 73.5 or something kilometers per second confirmed. But we have very nice explanation that maybe it's over cloud perturbation. So we don't say it's interstellar yet. But with with re-entry, you have the other end. So it's usually lower than 11 kilometers per second. But when, for example, with last week event, we have to look more into this. But I think what can be happening if you have a grazing event, like low slope, so it's grazing, it's a grazer so-called. What can likely to occur that it actually starts outside the field of view of a camera. And if it starts outside the field of a camera, you may think it's slow. But if you know, maybe it's already slowed down. So it has to be carefully looked. I didn't have so time yet, and we didn't get original data records yet from University of Malawi.
Not yet.
Yeah. So there are a few things you could distinguish, but also the first video which I was showing was we guessed it's iron. Even so, it's so unlikely that it's iron. It's usually like 1 out of 50 is iron. This is true for meteorites in museum, and this is now also true for meteorites, meteorite falls registered, because we have 50 and we have 1 iron. But with this one, we still guessed it's iron because it went so low threat, and we were thinking it's iron already when calculating because it was just so low, 11.28. Yes, so I mean, when you go through many events, you get some sense of some feeling. What is it? Some feeling, but usually very slow. Yes. And there are separate web pages I should share with you. Special web pages where they do alarm about space junk coming. Because there is special networks for space debris monitoring, and usually we do alarm about space junk. So you could also compare versus with alerts.
With this subject also, where in the plot alpha beta, where are the space junk?
Or it can be anywhere. I mean, I'll explain it like this. So look at alpha as mass, but then you have to correct by the slope and by the shape. So alpha is kind of composed of mass and size, shape and slope, trajectory slope. This is what's in alpha. So the bigger the object is, the smaller the alpha is. So the more you move here, the more likely you end up here. But then look at beta as material. Okay, it has more components, but one of them is material. So this is more or less, you see, the ice bodies composed of ice will be over here. So this will be big bodies composed of ice. This will be small bodies. Like I have a separate graph not published also yet, but maybe we do. When we analyze with radar, because the radar is so sensitive, we get super tiny dust particles. And when we get meteor showers, really, which are hardly sensible with any other method, and we got really clusters here. It's so nice to see. Like we get clusters in this upper corner area somewhere. Maybe I just did this. So we get these clusters for meteor shower. I think it's very nice, and it makes sense to me because it has super small mass, so it has big alpha, and it also has big beta because it's fragile and goes away.
So
with the junk will be, if it's made of iron somewhere here, but when usually I made it. Usually the mass is so that it actually manages to fully ablate in the atmosphere.
Right.
But I was doing, for example, Stardust CRC reentry capsule. I was just recently reviewing papers, so I was looking for this, my old abstract or what. Yes, and it gave good result. I think the capsule was maybe 48 kilos, and using this method, I get 45 kilos or something, which I think is very good.
this region here, right?
Well, the capsule was with beta probably zero. I don't know. So if beta is zero, it's I don't know. I mean, if beta is zero, it means no mass loss. It's a little bit off.
Okay.
If there's any other question, please let us, Maria. Again, thanks, Maria.